Hello out there in physics land. This is Mr. Zarzak coming to you not live but alive from Glenbard West Physics Studios. In this screencast, I'm going to take you through the calculations for the 2D kinetic energy analysis for the 2D momentum collision lab. So let's get started. Before starting your analysis, you're asked to diagram out your 2D momentum vector information from day one of the lab. This is just going to be a sketch, okay? And the sketch can be drawn by hand, and it does not need to be properly scaled, but it does need to include proper information. So just a rough sketch, alright? You're going to want to include the arrow line that you determined on day one for your momentum, okay, the angle between the two momentum vectors afterwards, and then somewhere maybe over off on the side, include the actual numerical values that you measured during day one of the lab. A couple quick notes concerning units and sig figs. Alright, when you're recording values for both your momentum and then later on for your energy, okay, you want to represent those values with the units that we actually used in the lab. Alright, for the mass, alright, our units for each of the balls is the ball mass unit. Now this is a fictitious unit because we didn't actually measure, and this is something that you were given. Okay, so you do want to maintain using this as opposed to talking about grams or kilograms, because if you use grams or kilograms, well then it's misleading. The same thing for your time values. Okay, all the balls were in the air for one clank. Okay, which again is an arbitrary unit. It's irrelevant what a clank is other than the amount of time that each ball spent in the air. Okay, because momentum is the product of mass and velocity, and because the horizontal component of your collision ball's velocity remains constant, okay, that's just calculated by taking the given mass of any of the balls times the distance that your team measured on the floor divided by the time of one clank. Okay, so when you're recording units for momentum, be consistent with the units that we actually used in the lab: BMU, clanks, and of course meters for distance. So momentum, or moving inertia, and kinetic energy are not the same thing, but that doesn't mean that they're not related. In the lab instructions, you're told that to find the kinetic energy, you can take your momentum values for both your initial rolling and then your target and your rolling after, square those, and then divide by 2 times the mass of whatever ball you're calculating the kinetic energy for. Okay, so why does that work? Well, if we look at momentum, momentum is just the product of mass and velocity. And so for kinetic energy, we're taking the momentum and squaring it, which means we're taking mv and we're squaring that, and we're dividing that by 2 times the mass of whichever ball we're determining the kinetic energy for. Kinetic energy then would be m squared v squared over 2m. Okay, and when I do this, notice that, well, one of the masses cancels out. And what are you really left with here? You're left with kinetic energy equals 1/2 mv squared. Okay, the formula that we're used to. So as far as what we need to calculate, again, just follow the instructions in the lab. Take any of your individual momentums for any of the balls, square them, and divide by 2 times the mass. Warning! 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 The marble only has 1/3 the mass of either of the other 2 balls, and so when you calculate the kinetic energy of that, you will square the momentum that you got from day one, but you need to divide by 2 times 1/3 m. That will affect your kinetic energy and hence affect your energy analysis, so be careful of that. To perform your kinetic energy analysis, you're going to need to determine the kinetic energy of the system before and then the kinetic energy of the system after. For the before, well, the only thing that's moving is that initial rolling ball. So that's your entire initial kinetic energy. And so to get that, you're just going to take that value from your diagram, square it, and divide by 2 times m. Okay, and that'll give you a numerical value for the kinetic energy before. And then for the after, okay, well, you've got 2 things contributing to the kinetic energy. You've got the kinetic energy of that rolling ball after, and you've got that kinetic energy of the target ball afterwards. Okay, so you're going to need to sum that up, and that together is going to give you your final kinetic energy. So for each of those values that you should have written down for your moving inertia after, square it, divide by 2m, and add that to the momentum of your target ball after squared, divided by 2m, and that'll get you that final kinetic energy. One final note on the energy is about the units. Okay, the units for the energy in this lab do not equal joules. Alright, joules are a kilogram meter squared per second squared, but we didn't use kilograms. We used ball mass units, and we didn't use seconds, we used clanks. Okay, so that affects the units. It would be misleading to represent our units as joules, so you do need to figure out the proper units for the energy, which will be kind of ugly, but also kind of hilarious. So take your time with that. Note in the instructions for the lab that you're asked to calculate the percent difference between the kinetic energy before and the kinetic energy after. Okay, the reason that we do this is because those kinetic energies are derived from the momentum values that we found on day 1 in the lab, and all those were measured values from the landing locations of each of the balls involved in the collision. So for the reason we do that is because we're comparing two known values, so percent difference is more appropriate here. How do you get the formula for percent difference? Well, it's in the science packet, and you also have access to the internet. And I'd say by this point in the year, you probably know the percent difference formula. If not, look it up. The 2D Kinetic Energy Analysis handouts has 3 blank pages, 3 glorious blank pages for you to use to show all of your work, and you're told explicitly in the instructions that you do have to show all your work for each of the collisions. Alright, so just as a reminder as to what that entails, that means that for each of these you need a diagram, which is just the rough sketch, alright, of your momentum collision diagram and data, including the air line and the air angle. You need your conversions of momentum into kinetic energy, alright, for every single kinetic energy value that you're going to use. You need the initial and the final kinetic energy values calculated. Alright, and you also need your percent difference calculation. Okay, and so you're going to repeat that, all these things for the steel padded as well as the steel marble. As for your conclusion, okay, much like the Air Tracks lab, the conclusion is going to be very straightforward. It says right here, which is it, and by which is it, it means which one of these does not show conservation of kinetic energy, and it is singular. Okay, so there's a clue. If you find that energy is not conserved for more than one of those 2 collisions, you might want to take a look back and double check those calculations. And most importantly, explain why. Alright, now here we're not just going to reference some percent difference number. We're going to talk about the physical why of this. You know quite a bit about collisions by this point, so identify what you know and tell me why for that collision energy is not conserved. As far as what gets turned in for this lab, okay, well, there's a team portion and there's an individual portion. The team portion is the 2D momentum collision lab, which really just means that's the big paper, okay, with your momentum diagrams, all your numbers mapped out. It's basically where you get your data, okay, for the part of the lab that's your individual portion, and that individual portion is, of course, this 2D kinetic energy analysis. Every team member is responsible for their own calculations for kinetic energy, their own percent difference calculations, and their own conclusions. Everyone's going to turn in their kinetic energy analysis along with one 2D momentum collision lab for the team. Again, everybody does the 2D kinetic energy analysis calculations on their own, showing all their equations, all their work for all 3 of the collisions, and then the 2D momentum collision lab, which is the big giant diagram with the momentum data and diagram. That's the team portion. Thanks for watching, and good luck with your calculations.